Okay, so in the formation of a solution, we can actually divide the process into three steps. So the first step will be breaking the solvent-solvent interaction. The second step is breaking the solute-solute interaction. And the last step is formation of the solvent-solute interaction. So the sum of these three steps is the dissolution process. So when you dissolve your solute in the solvent. Now, in any chemical reaction, we have what we call the quantity called delta H, which is the change in enthalpy. So simply put, the change in enthalpy is the heat involved in the chemical reaction. So for the whole process, the formation of the solution, we have the change in enthalpy for the whole process, or the delta H solution. And for each step, we have corresponding delta H values. So in here, we see a diagram illustrating each step in the formation of the solution. So what you need to remember is that when you are breaking any interaction, the sign of delta H is negative. So for our step 1, delta H is negative. For step 2, delta H is also negative. And for step 3, since instead of breaking interactions, we are forming interactions, the sign of delta H is positive. Now the values or the magnitudes of this delta H tells us about the strength of the interaction. So the magnitude of delta H gives us an idea of the strength. Okay, so the sign tells us whether the process is breaking or formation of interactions, and the magnitude or the value of the delta H tells us of the strength of the interaction. So we add the three delta H quantities to get the delta H solution. Now we can actually have two results for our delta H solution. One is a delta H solution that has a negative value, and a delta H solution that has a positive value. So if our delta H solution is negative, it means that the values of steps 1 and 2 is much greater than the value of step 3, meaning we needed more energy to break the solvent-solvent interaction and the solute-solute interaction than the energy created from the formation of the solvent-solute interaction. So, a negative delta H solution will arise if the sum of delta H1 and delta H2 is much greater than delta H3. So this is the absolute value. Now, if we have a positive delta H solution, it means that the energy created from the formation of the solvent-solute interaction is greater than the energy needed to break the solvent-solvent and the solute-solute interactions. So a positive delta H solution will arise if delta H3 is greater than the absolute value of the sum of delta H1 and delta H2. When we talk about solubility, the expression like dissolves like always pops up. So when we say like dissolves like, it refers to the interparticle or intermolecular forces of attraction that your solute and your solvent can form. So if the two of them can form the same type of intermolecular force of attraction, it means that your solute can easily dissolve in your solvent. So for you to be able to determine the type of the intermolecular force of attraction, you need to go back to your Lewis structure and your molecular geometry, because mainly when we talk about intermolecular force of attraction, the polarity of the molecule is very important. So let's try solving some examples to apply the rule like dissolves like. So the first one, we have bromine. So in which solvent will bromine most likely dissolve? Is it benzene or water? Okay, so you need to recall the Lewis structure of each molecule. So for bromine, diatomic bromine, we have this Lewis structure. So I won't be drawing the non-bonding electrons anymore. For benzene, so benzene has 6 carbon atoms in a ring with alternating single and double bonds, and each carbon is bonded to one hydrogen atom. Or a simpler way to draw the structure of benzene is like this piatos shape. Okay, then we have water, which has a bent geometry. So now we need to identify whether each molecule is polar or non-polar. So bromine, diatomic bromine, is non-polar, okay? So because we have a zero difference in electronegativity. For benzene, obviously it's also non-polar because it's symmetric. For water, we have polarity in water, and the polarity is directed towards the oxygen. So this is non-polar. Benzene is also non-polar, while water is polar. So bromine is readily soluble in benzene but not in water. Okay, so another example. So we have potassium chloride. So you know that potassium chloride is an ionic compound. Okay, so if we write the Lewis structure, we have this Lewis structure for an ionic compound. Now, carbon tetrachloride has tetrahedral geometry. So this is CCl4. And we have liquid ammonia. So liquid ammonia has a trigonal pyramidal geometry, and it has one lone pair on nitrogen. So again, we need to determine whether each molecule is polar or non-polar. So for potassium chloride, this is ionic. So it doesn't belong to either of the two classifications. For carbon tetrachloride, so the carbon chlorine bond is polar. So the bond is polar. The polarity is directed towards the chlorine atom. So we have four polar carbon chlorine bonds. But because of the tetrahedral geometry of the whole molecule, these four polarities cancel out. So the net polarity is zero, so carbon tetrachloride is nonpolar. On the other hand, ammonia is polar, so we have polar bonds directed towards the nitrogen. And we also have a lone pair here, which is also very electronegative. So the net polarity is pointing towards the nitrogen atom. So liquid ammonia is polar. Now, knowing these, in which solvent is potassium chloride more soluble? So the answer is liquid ammonia and not carbon tetrachloride. So why is it so? Because if you recall, we have a type of intermolecular force of attraction called ion dipole. So your potassium chloride can form an ion dipole type of IMFA with ammonia. So last one, we have formaldehyde in carbon disulfide and in water. So formaldehyde has this structure. Okay. Then we have carbon disulfide, which is linear. And we have water, which we have previously drawn. So it has a bent geometry. So now we're going to identify whether each molecule is polar or nonpolar. So for formaldehyde, there's also polarity in this molecule. So the polarity is directed towards the oxygen atom. So this is polar. Carbon disulfide is nonpolar, so it's linear. We have some polarity pointing towards the sulfur atoms, but due to the linear shape of the molecule, these two polarities cancel out. So carbon disulfide is nonpolar. Then a while ago, we said that water is polar. So formaldehyde is more soluble in water than in carbon disulfide. So we will discuss two factors that affect the solubility of a substance in a certain solvent. So these two factors are temperature and pressure. So for temperature, we will only tackle the effect of temperature on gaseous solutes. So for gases, the relationship is indirect. So we have an indirect relationship between the solubility of gaseous solutes and temperature. So the higher the temperature, the lower the solubility of your gaseous solute. So this is because when you increase the temperature, the kinetic energy of your gas molecules increase, and this allows the gas molecules to escape from the solution. Now, a very relevant consequence of this relationship is what we call thermal pollution. So, thermal pollution happens because of an increase in the temperature of water in a lake, for example. So, this can be due to the natural heating of the water climate change or due to factories that discard their heated water into lakes or seas. So the hot water causes the solubility of oxygen to decrease. So there is less oxygen dissolved in your water, and these cause this causes the fish to die due to lack of oxygen. So the second factor is pressure. So we will again discuss the effect of pressure on gaseous solute. So actually for solid solutes, pressure has minimal to no effect on the solubility. So for gases, there is a direct relationship, higher pressure, higher solubility of your gases. So this is very evident when you open your carbonated drinks. So because your carbonated drinks have dissolved carbon dioxide in them. And if you open your carbonated drinks, you are releasing, quote unquote, you are releasing the pressure. So actually, what is happening is that the pressure becomes equal to the atmospheric pressure. So there is a decrease in the pressure. And the decrease in the pressure also decreases the solubility of the carbon dioxide in your drink. That is why you hear the fizz when you open your soda. So another relevant consequence of this relationship is when carbon dioxide in lakes in the bottom of your lakes, um, the dissolved carbon dioxide in the bottom of your lake increases as time passes by. So it's increasing because we know that at the bottom of any body of water, the pressure is greater than the pressure on the surface. So the carbon dioxide in the bottom get builds up, and it reaches a certain point at which the dissolved carbon dioxide just violently escapes to the surface of the lake. So there was a certain incident in Africa. So this happened in 1986. So when the carbon dioxide escaped from this lake, so it caused a huge amount of carbon dioxide in the air, and people in the nearby villages got asphyxiated, and there were people who died from the incident. So, right now, they are trying to prevent this incident from happening again by slowly releasing the dissolved carbon dioxide from the bottom of the lake.